Imagine this. You've just poured billions of dollars and, honestly, years of your life into engineering the ultimate subsea flow line. The steel? Perfect. The seabed foundations are solid. Everything is online. But then day 40 rolls around, and the fluid inside that pristine pipe suddenly cools, solidifies, and forms an absolute brick of a plug. Just like that, your state-of-the-art system is entirely useless. You are instantly offline, you're bleeding revenue by the minute, and you're staring down a multi-week, multi-million-dollar remediation. Well, welcome to our explainer on system engineering and fluid behavior, where we're going to look at exactly how we avoid that absolute nightmare. Because of catastrophic threats like that solid plug, the discipline we're focusing on today, flow assurance, has picked up a pretty blunt nickname in the industry. People call it the lifeblood of subsea engineering. And look, that's not just a catchy phrase. The financial stakes of failing to get fluid safely from the mudline up to the host facility are just staggering. Because we aren't dealing with a nice, stable liquid here. Reservoir fluid is this incredibly complex, multi-phase mixture. Its behavior changes wildly depending on the pressure, the temperature, and its chemical makeup as it travels. Getting that fluid to the host reliably, every single day, for decades, that is the job. Okay, Section 1, the 3 flow domains. Let's dive right into the engineering toolkit, shall we? How do we actually fight this massive threat? Well, we basically break the problem down into 3 distinct, overlapping defense zones. In system engineering, flow assurance is split into these 3 coordinated domains: production system design, system integration, and equipment application. And these aren't just siloed departments that never talk to each other. They act as a deeply integrated safety net. Their whole combined purpose is to guarantee that fluid keeps moving under absolutely any operating condition. Smooth startup? Great. Normal day? Awesome. Sudden, chaotic shutdown? They've got it covered. Let's look at the first one, production system design. This is all about optimizing the thermal hydraulic performance of the system. Think of it as setting your baseline. You're sizing the flow lines, you're figuring out how much insulation you need, and you're configuring the pumps for your expected long-term flow rates. It's basically the foundational math to make sure the physical hardware can handle the volume and heat of what's continuously coming out of the ground. But, a perfectly sized pipe doesn't mean much if it's completely isolated. That brings us to our second domain, system integration. This is where we manage all the functional interfaces. We're coordinating exactly where to put chemical injection points, how the monitoring systems are pulling data, and how the control logic actually talks to the rest of the subsea production system. This domain ensures that the left hand absolutely knows what the right hand is doing at all times across the whole field. And then we have the third domain, equipment application. Because sometimes passive design, like just wrapping a pipe in a ton of insulation, simply isn't enough. When you've got declining reservoir pressure over the years, or you're pushing fluid across ridiculously long distances, you need active mechanical help. This domain is all about deploying active subsea processing and boosting hardware to forcibly manage the flow, rather than just hoping to passively contain it. All right, moving on to Section 2, steady state versus transients. This right here is the core conflict of flow assurance, and honestly, it's the #1 trap for new engineers entering this field. Let's contrast these 2 states because this is where the real engineering budget gets spent. Designing for steady state is kind of like planning a road trip assuming you'll hit 0 traffic and maintain 65 miles an hour the whole way, or packing for a flight assuming it's going to depart exactly on time. It's the easy, highly predictable scenario. But transient state, that is reality. Designing for transients means planning for the traffic jams, the detours, and the sudden emergency stops. It's packing for the version of your trip where the flight gets delayed 6 hours, gets rerouted, and you still need all your stuff to work flawlessly when you finally land. So what do those underwater traffic jams actually look like? They're transient conditions. Things like startups, shutdowns, unplanned upsets, blowdowns, and warm-ups. And during these events, pressure and temperature do not play nice. They don't stay in their comfortable, steady-state lanes. They swing wildly, pushing the environment way outside of that safe, predictable envelope. Which brings us to a massive warning. A steady-state only design is a dangerous illusion. It's a hugely costly trap. Your system might flow perfectly at a constant rate, sure, but the second you hit an unplanned shutdown, the temperature in that pipe plummets, and it is precisely during those transient swings that solids, like hydrates and waxes, love to form. If you didn't simulate for that chaos, your perfectly flowing line is going to plug up solid the very first time the system trips. Okay, Section 3, evolving field life risks. The plot actually thickens here because these risks aren't static. Let's look at how flow assurance risks constantly mutate over a 20-plus year lifespan. Let me ask you something directly. If a flow assurance design is rigorously tested and validated as completely safe in year 2 of a project, is it automatically still safe in year 15? What do you think? Yeah, the answer is a resounding no. Just look at the timeline of a typical well. In year 2, you've generally got really high reservoir pressure and a low water cut, which basically means there isn't much water mixed in with your oil or gas. But fast forward to year 15, and the physics are completely different. The pressure has naturally dropped off, and that water cut has skyrocketed. This totally mutates the flow regime. More water means your corrosion profile is entirely different, and crucially, your risk for hydrates and wax goes through the roof. Because of these constantly shifting variables, how many transient shutdown and restart simulations do you think engineers have to run for just one single deepwater tieback over its life? Dozens, literally dozens of incredibly complex simulations just to account for how the fluid's personality changes across the decades. So flow assurance is absolutely never a one-and-done deal. Because flow regimes change, corrosion risks shift, and hydrate threats multiply as that water cut rises, the whole design has to be continuously revalidated across the entire production timeline. You have to be dead sure that your chemical injection, your insulation, and your heating can handle the fluid not just on opening day, but 15 years down the line when the reservoir is tired and wet. Finally, Section 4, the ticking clock. As we wrap up this explainer, I want to zero in on the most critical, sudden, and frankly terrifying event a subsea operator has to deal with. I'll leave you with this to chew on. What actually happens to the fluid the exact second a subsea system trips and completely shuts down? Well, the flow just stops. That warm fluid from the reservoir is no longer feeding into the pipe. Almost instantly, the fluid currently trapped inside starts bleeding its heat into the freezing seawater surrounding it. A literal countdown clock starts ticking toward disaster as the temperature drops. How much time do operators really have before that fluid turns into a solid block of ice-like rock? And more importantly, how do they stop it? Well, we're going to uncover those exact answers as we explore the specific threats each domain handles, starting with erosion, in our next explainer. Thanks for joining me.